Hi, my name is Austin Carter and I'm from the University of Michigan, and today I'm going to be talking to you about how we can use strontium isotopes to understand subglacial grinding in meltwater routes in southern Greenland. So the Greenland ice sheet is a massive ice sheet. It's the second largest one in the world and only second to Antarctica. And it is home to a whopping amount of nearly 3 million cubic kilometers of ice. And so when this ice melts, the water percolates down to the base of the glacier and interacts with the minerals embedded into the bedrock. And as a product of climate warming, it's likely that we're going to see an increase in this water-rock interactions as meltwater contribution goes up. So we can't actually see with our eyes what's going on at the bottom of the glacier because there's so much ice in the way. So for this study, we're going to use strontium isotopes to tell us about the mineral weathering that's occurring underneath. And so for my study specifically, we're looking at a glacier, a specific glacier on the Greenland ice sheet called the Kusap-Surmier Glacier. And it's a land-terminating glacier, which means it does not flow into the ocean or a body of water, and rather it stops flowing on land. And the water underneath the glacier pools out at the end or terminus and creates this proglacial stream. And you don't necessarily want to be drinking this water anytime soon because it's very dirty and filled with sediment. So we collected samples every 3 days in August right here in the proglacial stream and every 2 days in September. And so the sediment that is floating in the water was separated out. So you have two components. You have the suspended sediment component and you have the component of just the water and everything that's dissolved in it. So the meltwater samples were taken to the University of Michigan where they were analyzed at the glaciochemistry isotope geochemistry lab. And the strontium was separated out and they were analyzed on a mass spectrometer. So for the first graph we have the time or the day of the year that each sample was collected, and we have the strontium 87 and strontium 86 ratio, both isotopes of strontium. And in yellow we have the suspended sediment, in blue we have the dissolved load. So what we see is a decrease in the dissolved loads ratio from about here to here. So there's just a giant decrease. And what's interesting to note is that there was a massive rain event that occurred here, a week-long rain event to be specific. And so what we can do is we can look to see, well, what's contributing to this proportion, or what's contributing to this ratio. And so we look at the proportion of strontium 87, 86 coming from nearby minerals. So a study in the past, Finch et al., 2001, has strontium isotopic composition data for alkali feldspars and apatite. So using a mixing theory relationship, we can calculate how much of the strontium is coming from these apatite and calcite minerals. So before the rain event, there's not a lot going on, and then the rain event happens and we see a spike in the strontium coming from apatite and calcite. So as we see a decrease in the ratio, we see an increase in the amount of strontium coming from apatite and calcite. Now this can be explained because rubidium radioactive decays to strontium 87. So minerals that have a lot of rubidium in them, like alkali feldspars, are going to have higher strontium 87, 86 ratios because there's more strontium 87. So minerals that have that strontium 86 substitutes in for, like calcium rich minerals like calcite and apatite, are going to have a lower strontium 87, 86 ratio because they're not going to have as much strontium 87 because they don't have rubidium. So we see this in our samples, and so the way that we can explain what's going on here is that this week-long rain event that occurred, the rain is actually dissolving apatite and calcite minerals from veins on these mountains and pooling down on the glacier and percolating down to the bottom and pooling out at the end. So it's interesting to see that these small effects in weather really do affect the chemical composition of the water in the area. So this study is a way of monitoring these weathering reactions using strontium isotopes, and it's also a way to determine the proportion of strontium of weathering of different minerals in this glacial watershed.